Oh, look, I can resume recording. That's great. Perfect. Everything's good to go. Get chat back open. I gotta say, this is some real time loss on the speed run, but we'll make it back. But anyways, yeah. So the summary of the situation is during. Yeah, I should restart the timer. God, I set up these hotkeys, but I forgot to. Okay, pause, stop, clear current time. I had everything hotkeyed and then I forgot. Okay, yeah, cool. So I've been given. Oh, I really hope that didn't enter a command. Anyways. All I know basically in terms of what things are going to look like tomorrow is that those are going to be problems just basically on Coulomb's law and vector addition, vector properties. This is initially going to look pretty substantially more advanced than the stuff we're going to be doing because there's going to need to be a lot of background before we get to things like gradients and divergence and all of that. Basically, the end goal of all of this is to sort of as quickly as possible get us to the point where that table I had at the end of my review presentation is actually a review. So you know what all of these laws are, how to compute gradient, how to compute flux, how to compute all these things, how they interrelate, and how to use all of that, basically. So during this time slot, as you can see, things are a lot more free. I basically just need to be here answering student questions for 2 hours. And as far as I'm concerned, as long as you guys are around, that technically qualifies as the implicit question of how do we do calculus, which I am graciously given this time slot to help answer in whatever manner I can. But yeah, basically during like the Dollar stuff, during actual class time, I am Professor Dollar's direct subordinate. It's my job to teach the class basically as he wants things run. And during this tutoring center hours is when I have a lot more freedom to actually explain things, which is, I don't think I'd be allowed to have a split timer in any official capacity for all of this. So to be clear, even though I'm working right now in college time, none of this is actually like official by the college. None of it's mandatory. None of it's graded. And I want to be incredibly clear. This is absolutely no impact on any official metric or diagnostic. As I said, I'm paid to be here by the college, and I am here in part because I am a TA for 7D. This is not run by Professor Dollar. It's not going to be run like his classes. That's not me saying that the way he runs his classes is bad. And that's me saying that the way Professor Dollar runs his classes requires preparation, and I do not have that. I am lacking in many things that Professor Dollar has, such as a PhD and preparation. So this is going to be a lot more sage on a stage, so to speak, which is the term for just people talking about math or physics. Yeah, I am also lacking in money, but I think Professor Dollar might be too. Professors aren't paid great. You don't choose this career because you are smart. Don't worry. No one, I can assure you, no one in academia is smart, or at least none of them are wise. If we were all wise, we would have left academia. Well, hopefully this can be cheer you up then. But yeah, with that out of the way, we can kick off the speed run. The run ends when all of you understand, like I say, that chart I put up at the start of our review session, and that's going to be over the next few weeks. I'm not going to keep a running timer going. My computer crashes more frequently than that. But let's start then with parametric functions. So parametric functions are our starting point because they're probably the easiest way to get into basically calculus on variable or on vectors. They're sort of the easiest form of the vector valued function to understand. And I'm going to stop screen sharing for a moment so I can go into a draw space. In the future, I will have the ability to draw off of an iPad. I don't have that going at the moment, in part because I'm lacking an iPad, which would be an important tool for this. It's en route. So expect my handwriting to suddenly and miraculously improve somewhere around week 2 or 3. But basically the idea behind a parametric function, or really any vector valued function at all, is that a function, whether it's a vector function or a regular function, just associates, it really is, an element of some set S1, which is the function's domain. It associates elements from some set to elements of another set. And functions are just anything which has such a well-defined association for some set onto some other set. And then, of course, we understand all the properties of functions as arising from this basic relationship, right? We understand that functions are invertible if they are one-to-one. That is, any given element S2 is an element, oh, I cannot draw, is an element of, our big S. S2 only has exactly one thing in S1 that maps over, not 2, right? And so that gives us invertibility. We get all our other properties from things we expect to, from facts we know about functions, right? And while we're most comfortable dealing with functions that map, real numbers to either the other reals, or sometimes you may have even encountered functions that map from the reals to the complex plane. I really don't know what the math curriculum's like. You've done complex valued functions, I assume? Cool. Just like you can map a function from the reals to the reals, you can also map functions from the reals to the complex plane. In principle, you could map functions from sort of any object to any other object. In principle, I could define the whose shoe is this function that takes arbitrary shoe and tells you whose shoe this is. So that would be a function, from the set of shoes to the set of people. It would be more specifically to the subset of people that own shoes, but the overall encompassing set would be people in general. Now, this isn't a particularly easy to define function. Sometimes there's arguments about who owns individual shoes, so it may not be all that well defined. Also, it's not mathematically useful in any way, shape, or form, which is a great metaphor for life, but is also makes it less interesting to study, which is also a good metaphor for life. So that's really the idea behind functions. Really, they're just from any space to any other space. So when we've learned how to do calculus, we've basically only ever looked at this case, functions from a real space onto another real space. So that's just your typical curve function. Does something like that. This is essentially one real space. We label it X, but of course, really, X is just any real number. Ooh, my R's are getting worse. And then Y, of course, is just another real number. So this function is literally just a mapping that's moving points over from one line to the other line, wherever they are. Right? And so with this idea of what functions are as sort of this more general object, there's really nothing that stops us from mapping the reals, for example, onto some other space. And a very easy choice of space to work in is R2. Has everyone seen this notation? Do you know what I mean when I say R2? Cool, yeah. It's R cross R. It's the vector space, two vectors, A, or two real numbers, A, B. Yeah, two-dimensional. Yeah, okay, cool. So you're familiar with the idea of higher dimensional real spaces. Yeah, it's just, and it does mean 2D. You can have 2D spaces that aren't R2. the dimensionality of the space is determined essentially by that square, because you could, for example, have C2, the space of complex valued functions, complex valued 2D vectors. So that could be like a vector that's like 1 comma I would be an element of C2. But we don't need to concern ourselves with anything other than R2 and R3. Sometimes we're going to be looking at surfaces, which are like R2, but for example, you know, we might have like a hill, right? And this is the world's ugliest hill. But I hope, you know, you get the idea of like some sort of weird curved geometry. And, you know, it looks like R2 if you look at a small section of it. Overall, it's not R2, but locally, it is R2. And you're going to hear me use that word a lot, actually, locally. This is because calculus, I think I said this possibly on last Thursday, but calculus is really the mathematics of taking local, by which I mean very small behaviors, things that are occurring in very small regions of space, and relating them to how things work over much larger regions of space, sort of global behaviors over, you know, intervals, like from 0 to 1 versus like behavior at exactly the point 0.5 and everything, you know, really, really close to that point. And so if we go on, we can sort of limit ourselves. We can talk about functions that map, and we put this little vector hat on top of our function to indicate that it really is a vector valued function that map from some space of the reals to, say, the vector space, to a vector space, R2, for example. And I'm going to sort of try and assume the notation that the variable we expect these things to use is t. And that's obviously meant to look like time. And there's sort of a very good reason for that, which is sort of the easiest example of one of these vector valued functions to think about is a function of time that gives position. Normally, we sort of think about functions as kind of being a function of a position, right? Like the function takes in as its input its position on an x-axis. But if you're dealing with a two-dimensional output, obviously it's going to be very hard. I can't like put t on this axis because then I still have x and y to put somewhere. So I'm going to have to put x in one spot, y in the others. Well, that sort of doesn't leave any room for another spatial coordinate. You know, I could put in z, but eventually we're going to want to work in 3D space as well. So sort of the remaining obvious coordinate to manipulate is time. And this, in some sense, it could be what sort of a dummy variable. It could just sort of not really mean anything, or it could actually be the passage of time. And actually, we're gonna think about this right now as actually being the passage of time. Because one of the most classic examples of one of these functions is what's called a parametric curve, a parametric function. I don't actually know why they're called parametric. That would require me to have like Googled this stuff before I started teaching it, and that, you know, isn't something I did. So we're all here. And yeah, yes, okay. It's just because it takes a parameter. I mean, all functions take a parameter. My stupid shoe example takes a parameter. Yeah, okay. They're saying, yeah, okay, so it's just off of parameter metric. I mean, it feels like there's got to be a better answer than that. Because like every function is measurable. Well, no, not every function is measurable, but the definition of measurability is a complicated mathematical claim which requires knowledge of real and complex analysis in the general case. Sorry, I do that sometimes. I say words I shouldn't. I got to get a sponsorship if I'm going to be drinking things like that on stream. That's out of an ad campaign right there. Though I imagine the people in the ad campaigns are better looking, but that's beside the point. That's unrealistic expectations. So to the point, So we have these ideas of these curves, and we can think about them, if we take like a simple example. At first, we're going to choose to make the x coordinate. How are we looking on using Twitch? I fiddled around with using Twitch, and I'm bad with computers. I may just post the recordings to Twitch because I can do that without making a fool of myself. So we can sort of think of this as like x of t. Yeah, we need to make text. I need to work on the tech for that, I guess. So we can think about these, right, as like the coupling of two separate equations, two separate one-dimensional functions. Yeah, maybe I can be the new face of that, though. I'm opposed to trying to destroy American democracy. I'm against destroying American democracy. So, I'd probably be better for that. I don't know. I don't keep up to date with what's going on, either on Twitch or just in the world. But yeah, we can think about this as sort of the easiest example to work with is let's just set x equals t for our starting position. This choice means that this can work. We can just say x equals t up here, and we can graph them in the usual way. Then we could have like y equals like t squared. And then basically what happens is we have, we'll also need to say what range t goes from. So we can say like t goes from, and there's like different notation that people are going to use for this, but let's say 0, 2 means that I want to look at t in that range. And then that just does this, right? Because like at each point in t, we look up, we say, okay, what happens at t equals 0? Well, we plug 0 in here, and we get like 0, 0. So we mark a point at 0, 0. And then we like try t equals 1, and we get like 1, 1. And we mark a point at 1, 1. And then we mark a point at like 2, 4. And we mark a point up at like 2, 4. And then, we do all the in-between points like 1.5 and then 2.25. I do have that memorized for reasons. And so on. We mark each of these points along this curve, and we use that to generate a curve. And this is the point where I'm going to stop using the whiteboard and go back to my full screen share, because now I went back to the whiteboard. This is why I'm not doing Twitch, because I'd be bad. So this is Mathematica. I've probably mentioned Mathematica before. I've shown it off before, I think. I'm going to be doing a lot of demos in this. Don't worry, you don't really need to understand what my code does. I'll explain whatever bits are relevant. If you ever pursue an advanced degree in physics, you will get very comfortable with Mathematica. Well, you'll develop Stockholm syndrome with Mathematica. Hell no on the advanced degree. Yeah, it's not for everyone, or like anyone really. So this is a simple example. We can see my choice of parametric function. This is my function here. So the x coordinate is time. The y coordinate is just cosine, or is just the x coordinate is just the time. The y coordinate is just the cosine of the time. And so indeed, we see the overall function traces out at each point, along my axis. At each time, I get a different height, and I use that, and I can plot out a cosine. And down here, I've actually prepared an animation where I show the actual process of it getting traced out. This looks really easy to make. It's not. Mathematica is not an easy language. So we're into, I should actually put the split now, because we're into curve plotting. We're looking at Mathematica curve plotting here. And we can see these arcs are traced out in this method. Now, as you can see, this is just another example where we see if we change like cos of t to cos of 2t, it does exactly what we'd expect. We plot it, and then this is just basically the y-axis. So this just behaves exactly like you'd expect a one-dimensional function to behave, or a function of a scalar, right? A function that produces a scalar, sorry, a scalar valued function. And then we go down. So you might be wondering, like, why do any of this? If I could have just done this by like just saying plot cos 2t across t from -5 to 5, if I could just do it the same way, why bother with all of this additional complexity? Well, the answer is I can plot something like this, right? So now the x coordinate is cosine of t, and the y coordinate is t. So we're just tracing upwards along the curve and producing the cosine curve along the x coordinate. You can't do this with a normal function because this fails the vertical line test. It fails the vertical line test a lot. There are actually an infinite number of points along each vertical line here. But by using a parametric function, it's still well defined, because we're defining this whole vector. We're defining each point as a function of t. So we're not getting into this issue. We can even do something that's sort of even more complicated than either of the two cases. You may have seen these pretty curves before. I'm pretty sure this is a Fibonacci spiral. I wouldn't know. I didn't look up how to plot a Fibonacci spiral. I just wanted to make a pretty shape, and I ended up with something that looks kind of like the Fibonacci spiral. And this, you can see the function up here is, it's a cosine in the x direction, and it's a sine in the y direction, except that I'm also widening them. Now, you'd probably not be surprised to see that if I remove these t's from that, I just get a circle. It just traces a circle, because, of course, x equals cosine theta, y equals sine theta is just the description of a circle. But by multiplying, wow, oh, I've got caps lock on, that's the problem. By multiplying by t, we get a circle, except the radius of that circle is constantly increasing, which is, of course, what a spiral is. I don't know why I have a second one, but I have a second one. We can even do this in 3 dimensions. And there's a reason why I didn't show off any examples in 3 dimensions when I was drawing things by hand, which is I can't really draw things by hand very well. And this is where we can sort of look at this. This function is a helix, right? It's a spring. And these are formed, as you can see up here, the function is just cosine of t, sine of t. So x and y are just cosine and sine, so that's just a circle. And then the z component is just t over 4, it's just t. So this is a circle, except we constantly move upwards. Where this is sort of a circle that's constantly being pulled outwards, this is a circle that's constantly being pulled upwards. And we can actually see this really well, and this is what I mean in my split timer when I say camera glitch, by lining this up. And you can see we've just got this dot spinning in a circle. So really we can just look at like the x and y behavior of this, and then we can also look at like just, oh, please obey me, work. This'll do. Here, it just looks like a sine wave, right? Like if I encourage those of you with laptops to physically pick them up and rotate them 90 degrees. And then this thing's gonna look like a sine wave. I do not encourage you to do anything which could break your laptops. Please do not sue me. But you can see that sort of all of these behaviors that are complicated in higher dimensional spaces really just look like lower dimensional behaviors, literally in this case, stacked on top of each other. This is literally just a series of circles that we're stacking on top of each other. So that's just the idea behind parametric plots. Really, what we are plotting, we plot out the full curve, but that red dot is the only thing that's like actually, yeah, that's actually being plotted. That's this expression. That's giving a single point, and that point is at that dot. And then this is like spinning a glow stick around, or anything else, or like if you swing a bright light around, it leaves sort of this traced pattern behind it. That's really what we're looking at here. And we'll address sort of a little bit more about that difference now, actually, because this is an important point. Cool. So now we're on to particle plotting, which is a parametric plot. There's a reason why I chose time as our axis, which is not just because we can display this over time, but because as we've learned in introductory physics, the position of a particle is basically just, it can be thought of as a vector, right? The displacement of a particle from its initial position is just a particle. Sorry, is just a vector, right? We've covered, presumably you've seen that before, and so it makes a hell of a lot of sense to give a function like this s of t here as of time to give the particle's position. That's just going to be vector valued. And so I've got an example here of s of t that you may recognize. It's vx of t times t is its x coordinate, and it's vy times t minus 9.8 times t squared over 2 is the y coordinate. Bonus points for anyone who can tell me what that is. A particle that's moving a constant speed in the x direction and whose y position is given by that. Yeah, exactly. It's projectile motion. It's just what happens when you throw a ball. And just like regular functions, we can take the derivative of vector valued functions. And the derivative of a vector valued function, I'm going to actually stop sharing and go back to my whiteboard here. Briefly, the derivative of a vector valued function is another vector. And as we know, the derivative of position with respect to time is just going to be velocity. And then as we know, the derivative of velocity with respect to time is just going to be acceleration. And every time we take the derivative of a vector valued object, we get another vector. And if we take the derivative of acceleration with respect to time, fun fact, there is actually a name for this, and it's named jerk. As it's not necessarily in the j direction, but that's j, jerk. And we call it jerk because jerk is the feeling you feel when acceleration suddenly changes and you're thrown to the other side of like a car because you suddenly had to make a turn. That's just your fun word fact for the day. Those of you who are also taking English classes or literature, whatever, may have better word facts than I do. But we make do with what we have. But yeah, that's what you feel. It's sort of the reason why, like, if you're in a like an airplane, you're just sort of gently pushed back into your seat, but it's not that bad. But you suddenly pound on the brakes, you're slammed forward. That's jerk. What you're experiencing is acceleration is in many cases not quite as uncomfortable as the derivative of acceleration is jerk. So I'm just going to ask you to sort of maybe take for granted that derivatives work this way. But if we think about the derivative of like some function that's a vector, x of t, y of t, dt, fortunately for us, we can just take the component y's derivative. So what I mean by that is we can just write this as the derivative of x. I can't draw of x of t up here, and down here, and let me know if, does everyone sort of feel like they could do this operation and feel like they're convinced that this is true? And it's okay if you're not convinced. In fact, it's probably better, abstractly speaking, if you find that kind of hard to believe, because I haven't actually done anything to convince you of it. I'm just telling you it's true. But this is where we're a little more relaxed. This is what I mean when I say this run includes glitches, because we're not going to, and is in any percent category, moreover, because I'm not really going to present a very strong argument for why this is the case. Instead, I think the best way to sort of imagine this is if we add vectors, right? If we have like v plus u, then this is like v1 plus u1, and then like v2 plus u2. So if you imagine changing v1 very slightly, changing v very slightly, you change v. A change in v is basically equivalent to adding a small amount of u in, right? It's like for a very small u, we're doing this. So we can imagine that changing v by adding on this derivative vector is done by adding the derivative in, and then we expect the derivative to be the derivative in the x direction, derivative in the y direction don't really interact, right? That's kind of what makes vectors manageable, really. And so now that I've presented a complete lack of convincing evidence of this claim, we can go down here and actually watch this in action. So this is the parametric plot of the projectile I had going earlier. If you've never seen an animated bit of projectile motion, this is what it looks like. It's relatively boring. Oh look, that's where I was testing my my speedrun splits. And here you can see this is just the Mathematica notation where I'm telling it to take the derivative of position with respect to time. That's just what all of these weird symbols mean. D is the derivative, function, variable, and then this is just to make this a new function. And we can see that we get out exactly what we'd expect. If we have this as our initial function, we know what the velocity should be. It should be that. And to our good luck, we see that it is. So now I can actually plot this derivative on this projectile, and you can see, I hope pretty convincingly, that the arrow always points in the direction the dot is moving. Arrows are a bitch to make work in Mathematica. They are not, you'd think this was easy, because it should be. So we're actually going to move on to our next category, or our next split, which is talking about really getting into what the calculus looks like. I've already sort of given you the peak of a derivative here. I'm actually not sure I get that one. I don't get you kids these days. Cool. So similarly, we expect that if we can take a derivative and get a velocity out of a position, intuitively, we want to be able to do the opposite, right? I mean, come on. Derivatives and integrals are best friends, right? They're just the same thing as each other, just in opposite directions. It'd be like me trying to tell you that you can do addition here, but you can't do subtraction, which I think that does happen sometimes, but that's not relevant to today. If you ever find yourself in that position, choose a new field, because clearly you're going into abstract mathematics and shouldn't be. We're way better than abstract maths. I say as a mathematical physicist. But yeah, we expect that if we can take a derivative, we can take an integral and get the same thing. So here's an example I've cooked up. So here's a function I'm giving as a velocity, which is just 2 times the time and then 4 times the time cubed. Now, we can define the position at any future point by taking the definite integral from time 0. And we need to know where this object started, but we can just assume that's going to be at the origin. You just move our coordinate axis so it does start at the origin. And we can integrate the velocity from 0 to whatever future time. So just some arbitrary time t. If we do that using Mathematica, because I don't take integrals by hand anymore, just as a matter of principle, then we get exactly what we expect, which is we get t squared t to the 4. And again, we can animate this. This animation is going to sort of look a little, it's going to speed up. As you can see, it starts moving pretty slowly and then really picks up the pace. And you may or may not be able to tell, I've plotted this position chart out as a parametric plot. This is actually a parabola. You might be wondering where exactly did we get a parabola from? The x-coordinate should be a parabola, but why is the y-coordinate a parabola if it's actually a t to the 4? Well, if we look at this, x is t squared, y is t to the 4, then really y is x squared, right? This is just the square of that term. So we actually still get a parabola back out from this object. And that's going to be pretty relevant later when we get to the nonsense part of our category. Ooh, no, I didn't want to click more there. So we're just going to take a pause and talk about why integration really means anything for vector valued functions, right? Because, yes, well, t tells you the time that has passed along the path. We're actually going to talk about how quickly it's moving. We can actually calculate the speed of this object by finding, if you remember that the speed is the absolute value of the velocity, it's the magnitude of the velocity. The speed's going to be the magnitude of the velocity vector. T tells you how much time has passed. X and Y tells you where it is at that time. And then when we go down here, this is kind of like taking a bright light and swinging it across a path. It'll leave like a trail, right? If you've ever like stared into a moving light. This is sort of the trail, or like if, the contrail behind a plane, which contrail is the right word, but we all know they're chemtrails. I kid. The idea being, so this is like this path traced out, and then this is the path. I'll use the phrase a little bit later. The dot is kind of like a pen tip. If you imagine drawing your path, that little dot you can imagine is like the tip of a pen that's drawing out your parametric curve. And depending on the physics we're doing, we're going to care more about the dot in some cases, or we're going to care more about the curve in other cases. And knowing when is which is entirely physics. That's a question of physics. And you'll learn how to do that in physics class. Learning how to extract information about the dot versus extract information about the curve, that's math. And hopefully you're going to learn that from me, but we'll see how that goes. So I want to take a bit of an aside though, like I was saying, on integration and differentiation on vector values and why that makes sense. Basically, if you remember what vectors are defined as these things that have scalar multiplication and addition. I don't know how abstract your linear algebra courses got, but a vector doesn't need to have coordinates, actually. There are vectors that cannot be expressed as some finite number of real or even complex numbers. Yes, linear algebra. Is that not something you've... Charming. Linear algebra was a prereq for my multivariable. Sorry. Yeah, it's a pretty important class if you're going to do physics. I'll let you in on a little secret. All of physics is just vectors. It's just linear algebra all the way down. Literally today in my advanced quantum mechanics class, right? So there's grad school quantum mechanics, and there's 2 quarters of that. And I'm in the second quarter, so it's advanced. We spent our time looking at how different operations worked on vectors. Just all day, it was just vectors. I do apologize for sometimes coming in with like asking you questions like, so, how much algebraic topology have you done on the, abstract finite terminating curve spaces? I apologize. I obviously went to a different undergraduate institution, and we had totally different prereqs and co-reqs set up. For us, linear algebra was basically a first semester course that you sort of took right off the bat, and then everything else assumed proficiency in linear algebra. And you can do a lot of things without doing linear algebra, I suppose. But we just went in kind of on the ground up with linear algebra. Yeah, don't worry about expectations from me though. In terms of things like, seriously, if I'm saying something and you're just totally lost, feel free to just tell me. I don't think anyone here is going to be embarrassed, or not embarrassed. You might be embarrassed. I can't control that. I should tell you you shouldn't be embarrassed. I'm just saying no one here should feel ashamed of not knowing things. Yeah, still worried about a test charge moving through an electric field caused by a point charge. That stuff will be tomorrow, more tomorrow than today, because sort of abstractly, the professor is going to want you proficient in a lot of things that you can probably fake your way through, basically. You can probably sort of do it. Oh man, I should get a copy of that textbook, shouldn't I? It's probably free online, right? I'm assuming you're all using it free online. I'll look for a free online. Cool. Yeah. I don't advocate for piracy. Anyone who's watching this recording to try and convict me of a future crime. Anyways, dear future lawyers, man, the future sucks, doesn't it? We're gonna, but we can sort of fake our way through doing all of this. You're all intelligent people, right? Don't feel compelled to agree or disagree on that. You are all intelligent people, and at the very minimum, you chose to sit and spend 2 hours listening to a underprepared graduate student lecture on a topic he did 4 years ago. So if that doesn't show a commitment to learning, I'm not entirely sure what does. So you're probably all good enough to fake your way through it. But I find that even though this stuff looks more complicated, right? You might be looking at all of this stuff and going, yeah, so when the fuck do we get to point charges? He's muttering about scalar multiplication and abstract spaces, but the answer is that you can get to the other stuff without this, but it'll be it's the difference between like looking up how to solve a problem online and just, skimming it and solving it, and learning how the machine works. And over time, just solving problems one at a time will get you to understanding how the thing works. But it'll get you there with a lot of pain and a lot of like fiddling with things and trying to work out why the integral is different this time than that time. Yeah. That's the other way you can tell this is, only semi-official. I'm pretty sure Professor Dollar doesn't cuss quite as much as I do in anything official. But yeah, I know, I swear like a fucking sailor. Except sailors have more class about it. But yeah, this looks a lot more painful, but really what it is not living in denial in some sense. And what I mean by that is if you're doing all the other stuff and you don't have this mathematical foundation, you'll find yourself in a position where you have to sort of press buttons until something works. And that's fine. And I totally wouldn't, I don't begrudge people who do that, especially seeing, you come in, you don't really have the preparation for this from other sources. But I personally feel like having the mathematical background makes things just easier. Obviously, I was a math and physics double major. Now I'm a mathematical physicist, which I keep saying a lot because I'm really proud of it. It's really cool to be able to say, oh yeah, I study topologically protected states of condensed matter. Like, it's just fun to say. It sounds like something out of science fiction. Like, a lot of my research sounds like something that would be said by some scientist in a film just before they turn on the warp drive. It's in actuality, it's way less cool, because remember when I said that all of physics was just vectors? It's all just vectors. How far are we away from warp drive? Well, the nice thing about warp drive is once you have it, you've always had it. I mean, I know that's time travel I'm actually talking about, but like, same thing, really. If you can get out of your light cone, you can travel through time. I mean, everyone could travel through time, but you can do it in the interesting directions. No one's impressed when you travel forward through time. Oh yeah, no, that stuff's fascinating. Sadly, I've never gotten really a chance to really do general relativity. Yeah, as you're probably pretty well aware, that's the sort of obvious trick for how we actually violate the rules, or we bend the rules to make it look like we're violating them. It should work. I do want to look a little bit more into that at some point when I have free time, basically because it feels like being able to do that should be able to make closed time-like curves. And closed time-like curves are bad. You shouldn't make them. The reason sorry, I was getting off topic, though admittedly, it's probably a little bit more interesting than the topic. So we can certainly take a bit of time loss here. Obviously, this isn't a real speed run. If it was, I'd be at the bottom of the leaderboards already. I don't have the words per minute speech to do this in an actual speed category. Yeah, actually, this is not quite where the nonsense begins. This is the calculus portion, which, yeah, it gets worse than this. I'm sorry. It gets better, kinda, but basically, so you've probably been told that a vector is an arrow with like a length and a direction, or you've probably been told that a vector is some number of scalars, some number of numbers stacked on top of each other, right? That's probably the definition of vector you've been given. That's hanging in the air like a threat, I guess. Is that can I get a yes or a no? That's what a vector is that you've been taught. Sorry. Oh, cool. Yeah. No, I was just saying yeah. Okay. That's kind of a lie. It's true that all of those things are vectors. It's not true that all vectors are those things. Other things which are vectors include all functions whose integral across all numbers of their square is a well-defined quantity. The set of square integrable functions across a space defines a vector space. This is because all a vector is, mathematically speaking, all a vector is a thing where we can do addition and we can do multiplication by scalars. Basically, something's a vector. Actually, you know what? This is me confusing you guys. Sorry. This doesn't matter. We're gonna ignore the fact that's the definition. This is an any percent run. Okay. Let me just hop over then to a whiteboard real quick. And I'm just going to call up Wikipedia real quick because I just want to make sure I get everything here 100% definitionally correct. Just you probably don't want to hear your teacher saying, let me just open Wikipedia real quick. But I just want to clarify my definition. Yeah. Basically, it's just a module over a field. So you take something called a field F. This is not a physics field. This is a math field F. And then we create a set V of elements, V hat in V, such that we have operation vector addition. So we have plus as an operation from the space of V cross V into V. We have scalar multiplication times, which is from F cross V into V. And we have a few properties of these things. We have a zero vector defined as, okay, yeah, cool. Yeah, this is getting really far afield. This is getting really into the weeds. Basically a mathematical field. So a field is a ring without zero divisors. So if we go a step deeper here, a ring is a group with multiplication, and a group is a whole thing. So there's a lot of built-in definitions here, but a zero vector is just any vector which has the property it's just any vector which, when added to other vectors, gives back the vector it's added to. So it's the vector zero. Except when we're talking about this in an abstract space, it doesn't necessarily have to look like zero. For example, it could be the function which returns zero at every position. That's the zero vector for the function space. So f of x equals 0 is the zero vector for the function space, which is L2 R. Yeah, no, it gets complicated. But basically a vector is anything where you can do addition, where the order you do your addition doesn't matter, where you have multiplication by a scalar, which this F thing that I'm calling a field is a fancy word for things that are like real numbers. So basically they're a ring where you do not have zero divisors. And what that means is it's somewhere where you can do addition and multiplication, and you can be pretty sure that if A times B equals 0, one of A or B is 0. That's not always the case. For example, in the integers mod 6, 2 times 3 equals 0. So that's fun, you know. But again, sorry, I am the worst at staying on topic. I truly am. Mod is like the remainder function, yeah. So all of this builds out of an idea called in something called group theory. And group theory basically takes this idea of addition, and it starts thinking about the properties of addition. And this is something I was actually about to cover in my original lecture, which is a lot of times in both mathematics and in physics, developing new ideas comes from taking ideas we already have and either applying them to a new subject matter. So like we're now learning how to apply derivatives to vectors instead of to instead of to functions, or rather instead of real valued functions to vector valued functions. So looking how a number changes over time, we look at how a vector changes over time. So a lot of the time we either do that or we sort of go the other way, which is we take an idea we already have, like something like addition, right? We take this idea of like addition on the natural numbers, 1 plus 1 equals 2, yada, yada, yada. 1 plus 1 equals 2, yada, yada, yada is basically how you explain a math degree. But you take these ideas and you sort of remove the restraints. You remove the object you were looking at and try and look at the properties of just what it means to be addition in an abstract sense. And that sounds like something you'd say while high off your ass. And in some cases, mathematicians were, but it's actually very well defined and rigorous. An example sort of this notion is I've mentioned a couple times that I study topological physics. A lot of people may have heard the word topology and not really know what it means. Basically, topology is the study of sets, and it starts with a very simple definition, which is it changes the definition of an open set from being, an interval. The normal definition is just like an interval that doesn't contain its endpoints. And it changes that definition to a set is open if I fucking say it is. And then we go from there. I mean, it's a little more complicated than that. We basically take the properties that happen to occur on sets that are formed out of intervals that do not contain their endpoint, and we go from there. But we basically strip out that definition, and that's how we start doing cool math, like this Klein bottle I own here. If you've ever seen a Klein bottle before, here's a nice pretty glass Klein bottle. Oh God, no, none of this is necessary. We just got really off topic. Sorry, because I'm terrible about staying on topic and people started asking questions. No, God, no. Sorry, I'm really sorry. I've gotten really off topic. Yeah. No, it's good. No, seriously, thank you. We gotta stay on topic. Gotta stay on brand here. So we gotta talk about, God, no, it's not green theorem time yet. This is, I think I'm getting too in depth, quite honestly. But the point is that we can do operations on vectors because they look like scalars. They look like scalars for multiplication and addition. So if you've ever seen, you've seen the definition of an integral before, right? You add up all these little values over increasingly small widths, and you do that over increasingly many small rectangles, right? This is sort of this traditional Riemann integral, or Riemann integral, sorry. It's a Riemann sum, Riemann integration. And it turns out if you just replace your scalar with a vector, everything else works. You can multiply your vector by a small like length factor, and you can add vectors together. So you can go from fail to veil without any changes to your formula. So we can just do vector integration just like we'd expect us to be able to do it. So you can really integrate anything where you have addition and multiplication by real numbers. And now we head over to the nonsense. Two different parameterizations can actually produce the same curve. This is a parameterization of a parabola from time 0 to 4. If we remember up here, our position function, same curve, right? And that was this thing from 0 to 2. So like, what gives, right? So how does that work? There's a few different reasons. Remember that we're really modeling pen tips. And we've seen this one. This is the pen tip of our position function. And then this is the pen tip on our parabola. You might notice, scrolling back and forth, that they were actually moving at different speeds. I'm actually able to plot them on the same graph. You can see that, that they follow the same path, but one does it much quicker. But when we're looking at these trails that are left behind, the speed isn't going to be captured inside that trail. The other possibility is that they're actually moving in opposite directions, right? So you can have the same particle moving in the opposite direction. Putting them together, this is what it looks like, right? Same path, different direction. And these trails don't capture the idea, even though the pen tips do. This is what I mean when I say there's some nonsense going on. Basically, parametric functions contain two sets of information. There's the geometric information that makes up the total curve across an interval. When we're studying that, sometimes we also care about the direction of the curve. When people talk about an oriented curve, that means it's a curve with a direction. It doesn't have a speed, but it does have a direction. That direction is what's meant by orientation. It means it has a forwards and a backwards instead of just a curvewards. And then we can talk about the properties that are held by that curve, not by the pen tip, but by the curve itself. Example of that would be the length of the curve that a parametric function traces out. And that's actually a very important one to understand. That's what's called arc length, because it's the length of an arc. And then there's sort of the local information on the pen tip and how it moves. And an example of that would be the speed of the particle at some given time. Depending on what we're doing, we may only care about one or we may only care about the other. And in order to extract some of this information and other bits of that information, we're going to use something called a length element. We're probably going to hear a few different names for this. It's basically, it's the velocity. So if I go to my whiteboard again, and we go to a new page, we have some idea. We have this particle, and it's traveling along some path. At this point, it's traveling with some velocity v, which is the derivative of the curve with respect to time. Now, let's say I asked you, how long is this curve? We'd need a tool to determine that, to determine length. Now, this is where these ideas of calculus as studying very local behavior and turning it global really come in handy if we want to talk about the length of this curve. So we can imagine that we can find it by adding up the length of like all of these tiny little segments, broken along each, passage of time, T1, T2, T3, just like, we could break up a curve like this into all the heights at different time and then fill in to get the area, right? Same idea. So, if we zoom in on one of these curves, one of the fundamental assumptions we're making here is that our curve through space is differentiable, is smooth. And that means that locally, if we zoom in enough, our function's linear. The closer in we get, the closer in that linear approximation is going to be to working. So, this still has a slight curve, but then eventually we get to like a purely linear solution, right? And that's what's meant by a derivative. It's that linear solution. Now, if I ask you to calculate the length of this line, right, and we had our x and y axis, you could do that pretty easily, right? We remember the rule, which is, if we look at this length here, and we'll call this dx. The d at the start just stands for differential or very small. And here dy, which is again, differential or very small. And then here ds, s being length here. This is easy, right? We get ds equals the square root of dx squared plus dy squared, right? That's Pythagorean theorem. Pythagoras' equations. So we have this, right? And remember when I said that this length element, remember this like little line here that we do by zooming in, that is exactly the derivative. So how do we rewrite this? We could write this as dsx, the x component of our s, dt squared plus and this actually looks like something you've seen before, though you may not realize it. It may be easier if I put it in a different notation, which is, remember, dsx dt is vx. So this is vx times vx plus vy times vy. And these are vectors, or rather, these are the components of vectors. These are not vectors, my bad. So do you know what this looks like? Can you tell me what this sort of resembles? Is there any way we could just write this in terms of V as a whole? Exactly. It's just the dot product. This is just v dot v. It's just the dot product. In other words, if we take the dot product of v, which is ds dt, and we take its dot product with itself, and we take the square root of that whole thing, we get the change in the arc length with respect to time. And of course, this is also perhaps less obviously, but just as convincingly, this is the dot product of the derivative squared, the square root of that. This is just the magnitude of the v vector, is the arc length, the change in the arc length with respect to time. And of course, the magnitude of a velocity is just a speed. And in some sense, we've just constructed the mathematical argument for the claim that the derivative of distance traveled with respect to time is the speed, which is the absolute value of the velocity, which is the derivative of the position with respect to time. And this is what we talk about. This v vector is this differential length unit here is just the differential element which sort of composes this curve via its integral. And so we can compute the length of the curve simply by integrating from some initial to final time the speed. So let's go back to our big overview, to this. We'll do this. Let's ask ourselves what the length of this curve is. We take the velocity function, we get this. And we take its dot product with itself, we get this. We take the square root of that to get its magnitude, we get this. It turns out this is actually simplifiable to this, 1 plus t squared over square root of 1 plus t squared, sorry. So if we look up here, perhaps you can find this convincing by seeing that it moves at speed 1 outwards, right? Its length outwards is increasing at a rate of 1, and its movement to the left, or to the plus theta direction, its curling speed is going to be proportional to t. Maybe that's not obvious, but that's how we're getting there. And when you learn how to do derivatives in polar coordinates, that will become incredibly apparent. So we get that. And we can just then calculate the length by integrating that differential change in length from 0 to some final time. And we get this thing. That's not really supposed to look like anything. Don't worry. In fact, sort of does what we expect it to do. This thing's speeding up as it's moving outward, so we expect the slope to be increasing. And of course, this function should never decrease. The line should never get shorter. But that raises an interesting question. If we know the speed, could we rewrite our function so that its speed was constant, right? Could we just adjust its speed at each point to produce a constant speed? No, we can't. If you try and do that, you get this stuff. And this is what I mean. This is an arc length parameterization. The idea trying to replace this t variable in the input with an arc length parameter to do it off of that. You can't do it. I mean, you can in special cases, but as a general rule. We can incidentally make a side note here about acceleration in the dot product and prove that the acceleration in the direction of motion changes your speed, where acceleration perpendicular to motion does not change speed. Have you all been sort of told that fact before? That if you're accelerating forwards or backwards, you're changing your speed. But if you're accelerating perpendicular to your direction of motion, your speed remains constant. Have you ever sort of been told that? And do you know why that is? Have you ever seen why? Vector projection is a good answer, yeah. But you can actually show it. The proper way to do it is with calculus. You'd want to show that the derivative of the magnitude of your velocity with respect to time is, so that's going to be the derivative of the square root of v dot v with respect to time. And I do not know if you believe me on this, but I would ask you to. You've seen the chain rule before, first of all, so we chain rule. And the chain rule works perfectly fine when you're dealing with vector quantities as well. Then we can expand this component. We know this. And this can be proven by breaking this down into its component form. And we would see that it is equal to 2 and then, yeah, it just happens. Now this claim requires that our dot product basically work the same way as scalar multiplication. And the reason dot product works like scalar multiplication is because the dot product is just scalar multiplication plus some addition. And because that's what the dot product is, we can just take that shortcut. We get that. And then, of course, here we get that this is equal to 1 over 2 mag v. And then we can cancel these 2's. And we can cancel this mag v by saying that this is v hat, the unit vector pointing in the v direction. And boom, we get exactly what you've been told. If you're accelerating in some direction, the rate that your speed changes is proportional exactly to the component inside. You see why it's a dot product. And then, like someone said earlier, then you can just do the vector projection, like Rio said. And that's an example of a situation where you can do vector calculus to get sort of a known result, and that's how you get that result. And it's actually not that bad a calculation. So then we want to talk about like how we integrate across a line. We can't really define integration across a line without defining functions across multiple variables, which will be our next week's topic. In order to integrate across a geometric curve, since we can't really do this arc length normalization without without being very lucky and getting something that can be normalized easily. Instead, what we can do is we can use U substitution, basically, right? If you remember U substitution, it works by saying some integral dx is equal to du dx is dx du du. Ugh, I hate U sub. But the idea is we can replace ds in an integral with ds over dt times dt, where ds here is the change in arc length, is the change in that vector. Sorry, is the change in your position vector. This is just the velocity. It's just the velocity of parametric motion. So if we're integrating across basically some parametric motion here, then all we need to do is use this velocity vector internally and then just integrate with respect to time. And so now we take integrating across some line, which might be really hard. You know, it may be hard to conceptualize like integrating across a circle. Like what does that even mean? Well, by replacing this weird integral with just our classic definition of integration with respect to a scalar and then a velocity vector in here, we skip over having to really do all this complicated stuff. We eliminate like all of the dot information, and we're just left with like this curve information just by sort of doing this replacement. Often when we're dealing with this thing, we care just a little bit more than just the overall shape of the curve. We also care about which direction we're moving. If there's a start point and an end point, we care about which one's which. It's really all we're doing. And fortunately, turns out ds dt has a sign, right? It's a vector and it can be in one direction or the other direction. Done. It's contained in there. The magic of math means we don't need to care. Prepackaged inside what we mean when we have this ds dt element. And finally, I just want to talk about closed curves. A closed curve is just any parametrized curve, any parametric curve, which starts where it begins. This is where orientation is particularly important because there's no start point and an end point. There's just a direction of motion. This could be like an infinite motion. This could be like the orbit of planets, the orbit of an electron around a proton, like in an atom. This could be any number of physical systems that sort of repeat infinitely. So here's the parametric plot of a circle. As you can see, I've taken the convention to start at the x-axis and then move along the y-axis, but I could have started from anywhere. Like if I start my video from here, say, aside from the little stutter at the start, which you may or may not be able to see, really any point could have served as a start point or as an end point. It's just an infinite loop. Much like my little Ouroboros bracelet. And so the only thing that really can be considered a sort of property here like start and end is just direction of motion. In this sense, counterclockwise, in this sense, clockwise. And that's just what's meant by a closed curve. The other important thing to note about closed curves, closed-oriented curves contain volumes. What that means is you can see there's an inside and an outside to this circle, right? Because it forms that loop, it forms a boundary between an inside and an outside. The same thing happens for a two-dimensional, because you can parameterize more than just a one-dimensional shape. We'll talk a little bit about two-dimensional parameterizations. A parameterized sphere. I'm trying to look around if I have any spheres lying around. I'm sure come on, I've got to have something roughly spherical on my table. I do not have something roughly spherical on my table. You know what a sphere looks like. I don't need a demo to explain, this is a sphere. Can you say sphere? Also, I have Mathematica. Boom. This is a sphere. Ever seen one of these before? Do they have them in your homelands? The idea is there's an inside and an outside to the sphere. And basically that exists because this thing is closed. There's no edges on a sphere. I mean, there's an inside and an outside edge, you know, but it's not like a mug, right? Where there's a boundary. Like there's not, when I say that I'm like drinking something from inside a glass, it's not really inside a glass. I could pour it out. You know, a bottle, you can have an inside of a bottle. You can't have the inside of a glass. That's because a glass isn't closed. Not all closed surfaces, though, contain volume. Remember my beautiful Klein bottle? This Klein bottle is what's known as non-orientable. You know how we've got these arrows? You can't do that for a Klein bottle. If I started moving along the outside of this Klein bottle, I would follow along this curve here. I would dip inside, and then I would be on the inside of the Klein bottle on my next loop, and then come back outside. As a result, there is no such thing as an inside or an outside. This shape actually only has one surface. Even though it looks like a sphere, you know, it has an inside surface and an outside surface, this doesn't. It just has a side surface. And that's what's meant by orientability. If you can have these like continuous direction of arrows, you can say, okay, I'm traveling along this side, and whatever's on my right, that's my inside, or whatever's on my left, that's the inside. But if you can't do it in 2 dimensions, you can't do it to a circle. But you know, if you take some shape like a Mobius loop and you twist it, it can contain an infinite amount of water. Well, sort of. I suppose you could consider the universe as being contained inside a Klein bottle. It's really the only self-consistent choice of volume contained within the Klein bottle is the entire universe or nothing. One could argue that everything is inside the Klein bottle. In fact, our universe might actually be what's known as an Alice universe, which means it might have wormholes that do not preserve orientation, in which case the entire universe would be shaped like a Klein bottle in some sense. This matters for theoretical physics because things break. Turns out if one were to pass through that wormhole in a certain way, basically every part of you that was positively charged would become negatively charged, and every part of you that was negatively charged would become positively charged. Except really nothing would change. It's just that charge would like positive versus negative would no longer be well defined. Because 2 paths would take a particle of the same charge, and without ever changing either particle's charge, they'd arrive at the end of the path with opposite charges relative to each other. And the way to think about that is like a Mobius loop. If you started pointing in one direction, came back around, like your orientation would be the opposite direction, but you never changed your orientation around the loop of the Mobius strip. It's just that single orientation is not defined for these objects. But for a closed surface which has an orientation, it has an inside and an outside, and that's what matters. I've been talking now for an hour and a half, but I think we're good to take questions. And please take as long as you'd like to formulate your questions while I grab a little bit to drink. My throat is parched. You never think about it, but lecturers talk like an hour and a half. It's actually a lot. Yeah, I'm glad to hear it. I wish I had sort of like made some problems. for all this. But basically, like that, this is the idea behind like a parametric curve, right? And the important thing to remember is that like none of this is scary. It looks really cool, right? It lets me do wizardry, like make these cool Fibonacci spirals. But a Fibonacci spiral, this really cool and pretty mathematical thing, is just like two separate equations here. And I could even just plot these things as regular equations. Could just say like plot that. And that's like the x component plotted out. And I could just like do that for the y component as well. Right? And these two plots, I mean, they're weird, right? Because who the fuck multiplies cosine by an increasing constant factor? I mean, you've got to be kind of a monster to do that. But you know, it's still just a nice old normal function. And two nice old normal functions make something pretty, like this. And if you want to do parametric, motion of like a thrown particle, it's just like it's parametric motion. It's just quadratic in one direction, or sorry, projectile motion. It's just linear in the other. It's like just throwing a ball. And you can like solve, like where will the ball be, for example, in after like 3 seconds of this? I can just like, it'll be there. I'd need to say, well, let's say, I threw it with a speed of like 2 in one direction and then like 8 in another direction. I could just get the position at the end of 3 seconds. Of course, it'd be underground at the end of 3 seconds because things actually end up falling pretty quickly. Like at the end of like 1 second, I could do the same thing for like velocity. I can ask, how quickly is it moving? And it's just taking some derivatives of regular old one-dimensional functions and then just, putting them together in a list. That's sort of all that's going on here. And we can do calculus in this environment just like we can do calculus in any other environment, basically by breaking down all our vectors into just stacks of scalars and looking at them as stacks of scalars. And remembering that, any vector operation that we define, like, cross products, dot products, that's just scalar products, right? Like, let's say I wanted, to like have like some vector, and I had like some vector v, and I wanted to take its cross product with like 1, 0, 4, right? Cross products are defined in 3 dimensions. And I just took this derivative. Well, we remember what a cross product is. We have I, K, Vx, Vy, Vz, 1, 0, 4. And we go through and we see this is 4Vy times I hat minus 4Vx minus Vz j hat. And then k hat is just minus Vy k hat, right? And then we just we take the derivative of Vy, we take the derivative of Vx, we take the derivative of Vz, and like all of those are just scalar derivatives. Even something, as complicated looking as a dot product, even if we had like, this wasn't 1, this was like some other function, f, then we just need to go through here and then put f here, and we just, now it's just the chain rule here, or not chain rule, sorry, product rule here, and we just use the product rule, and that's all it is. Because, the chain rule still works. We can still look at this as like some other derivatives, and we can say, well, let's look at each piece, individually, and pretend our derivatives are fractions, and write them as, dv dx is dv dx dx dt, is like dv dt dt dx, right? You just like put in any number of like intermediate steps, all of that. It all just works. It all just works. But I feel like I was going on a little bit of a rant there. Yeah, I'll leave the floor open for any further questions. And please do not ask me what vectors actually are, because vectors are actually really scary things. What is the highest calculus that you should know? I don't know the curriculum too well, but from my own experiences doing electromagnetics, when I said that we were building towards that table at the end of my lecture, at the end of my review, that table of like the three theorems, those three operations, I firmly believe that that's the ideal level of understanding. Next week will be Green's theorem in lecture, or in discussion. Yeah, lots of partial derivatives. Big secret, all calculus is partial derivatives and total derivatives. That's an important lesson you learn taking on, an advanced like math, advanced physics, whatever. Like all of the advanced stuff is really just built out of doing the simple stuff a bunch of times under specific cases or using special rules. There is, in some sense, there is no mathematics more advanced than addition. Everything boils down to addition and special rules. Yeah, derivatives of functions of x, y, and z. And then you're going to need to learn curl, divergence, and gradient. And all of those are defined just by those derivatives. And you're going to need to learn how to do line integration. And line integration, I actually just showed you already how to do it. If you're integrating some function across a curve, what you do is you use the parametric function to convert that curve into a, you convert like all of your positions into, like if I can very quickly show off what we'll be getting to with that. The idea is if you have like f of x and yeah, it kind of is. It's like the idea is if I'm integrating across some curve S, and S is like some curve. If I'm doing this, then I'm just taking the integral across t from, not to f. And now x, remember, is part of our parameterized thing. That's just and when I was talking about including that length element, that ds dt, that's essentially happening in here in this substitution here. That's sort of what generates that substitution. well, actually, no, you still need it. You need, in this case, it would be a magnitude. And that's our idea. And this is a magnitude because this is a scalar. If this was a vector here, if this was a vector function, then we'd take the vector form of this so that we could take a dot product. And some of the specifics about why we do it one way and not the other is beyond the scope of what I can really explain in short period of time. But the idea is this is sort of, yeah, build up to this idea of line integration is integrating a function, replacing each of its vector inputs with a parameterization, or a component of a parametric curve, and then sticking on this bit at the end. And this bit is important because, as we saw, there are multiple ways of parameterizing the same curve that get different results, right? That move quicker or slower. You might have a super fast, or you might have a very slow moving thing. This integral, this TF, is going to change depending on your speed. So in order to make sure that our result is purely geometric, is not something that cares about how quickly we move, we include this component. Because when TF is small, we're moving quickly and this thing will be very big. And when TF is big, then this thing is going to be very small because we're moving slowly. So these will like counter out, and all we'll be left with is the geometric form. Because like this big means this small, this big means that small, all of it will cancel out. So that's going to be how line integration works. You know, this bit right here kind of talks about, you know, this curve motion in terms of sort of values at the pen nib. And this thing here represents adjusting the pen nib speed to make sure that we're in the geometric case. Because the other option would be to try and do something called arc length normalization, which is the process, or arc length parameterization, which is the process of ensuring that we're moving at speed 1 throughout the entire process. And doing that requires finding the inverse of arbitrary functions, which is a non-trivial mathematical task. It also requires the integral of arbitrary functions, which is another non-trivial mathematical task. And it looks like Max just left, and left me as host. Doesn't matter for anything, just FYI, so I may need to monitor that no one shows up. I mean, we're about at the end of the time. Thanks for hanging out with me, guys. I know this was a hell of a lot more boring than the pitch probably seemed. Probably felt like we were going to be doing a lot more fun, zany activities and things. And then at some point I started droning on about arc lengths. But I like to think we have fun here. And there comes in my StatMech homework. That's going to be so much fun. Let me cut my video. Yeah, absolutely. That's the other half of the reason these tutoring centers exist. If it's going to be a question about like what material is going to be covered and all that, I can only give so much information because I only know so much. But if it's like, how does something work, or like, how things work, I'm absolutely able to.
I don't know if you have, if you can like view the classwork or anything, but it was about classwork 4.
Okay, since we're talking about classwork now, I'm just gonna stop the recording before we go on.
Yeah.
Just in case you don't want to be recorded asking about like classwork.